Tonight, we're going to explore a world that stays hidden from our everyday view. It's a place where the familiar rules of how things work just don't apply, a realm so tiny it shapes everything around us. We won't be looking at vast star fields or deep canyons. Instead, we'll gently journey into the very fabric of existence itself, where particles behave in ways that seem utterly impossible, where a single, invisible ripple can affect something light years away. This is a quiet exploration, a chance to simply wonder at the fundamental strangeness of our universe, allowing these profound concepts to simply drift through your mind. The basic ideas we rely on, the ones that explain why a ball falls when you drop it, or how a clock keeps time, those dependable concepts, they actually start to bend and twist when you zoom in really close. Imagine shrinking your perspective down, far past the size of a dust mote's, past the smallest cell, even smaller than a single atom. What you find there isn't just a miniature version of our normal world. It's a completely different landscape, governed by its own set of deeply puzzling principles. Things don't move in neat, straight lines at this level. They don't have a clear, precise path you can plot out. Instead, they act more like hazy, indistinct clouds, their exact location and movement only described by likelihoods. It's as if they haven't quite decided where they want to be, existing in a kind of blurred state until something makes them pick a spot. This isn't about faulty measuring tools or our lack of information. This is how the universe fundamentally works at its smallest scales. Causes and effects, which we usually think of as a very clear chain of events, become much less direct here. An event might happen, and its precise reason can feel elusive, almost as if it materialized without a strict command. And sometimes, impossibly, two completely different outcomes can exist at the very same moment, side by side, until something, some interaction, forces the system to commit to just one of them. This profound change from the solid, predictable world we know to this soft, probabilistic one, is why quantum physics can feel like stepping into a secret dimension. One that's always been there, quietly humming beneath our ordinary reality. It's not that the older, more classical ideas were wrong. It's simply that they only ever told part of a much larger, much stranger story, a story that holds everything together in ways we are only just beginning to truly grasp. Most of us will never actually ever see this quantum world. Its basic building blocks, the particles that make up everything, are incredibly tiny, far too small for our eyes or even our most powerful microscopes to ever directly observe. Think about it. They're smaller than the wavelength of visible light itself, which means light simply passes right over them without truly interacting in a way that would allow us to perceive them. So, these fundamental elements remain perpetually hidden from our direct sensory experience. Yet, even though they are unseen, their behavior, their peculiar dances and interactions fundamentally shape every single thing we encounter. They dictate the properties of the chair you're sitting on, the air you're breathing, and even the complex biological processes that allow you to exist. In this realm, particles don't simply zip around like miniature billiard balls. They ripple and drift, much like faint disturbances on the surface of a vast, calm pond. Some particles might pop into existence for the briefest, most fleeting moments, only to vanish again almost immediately. Others might behave as though they are in several places at the same time, existing in a kind of quantum ambiguity. The rules that govern this secret world are written in a language of mathematics, so abstract and unusual that even many experienced scientists who work with these equations openly admit they use them effectively, making accurate predictions without claiming to fully feel or intuitively understand their deeper meaning. This isn't merely a smaller version of our familiar world. It's a reality built on fundamentally different principles, ones that often directly contradict our common sense and our everyday expectations. And yet, this invisible world, quietly carrying out its intricate patterns and processes, is absolutely essential. Without its silent work, the entire visible universe, everything we can see and touch, including you and me, simply could not come into being. Energy itself, the very stuff that powers everything, isn't a smooth, unbroken flow. For a long time, back in the late 1800s, many brilliant minds in science thought that energy worked like water pouring from a tap, a continuous stream that you could divide into any amount you wanted. But then came a profound realization, a truly shocking discovery that completely changed that view. Under certain specific conditions, energy isn't continuous at all. Instead, light, heat, and all other forms of energy are actually made up of tiny, distinct, indivisible packets. These packets are called quanta. A quantum represents the smallest possible unit of energy that a system can either gain or lose. Think of it like the smallest coin in the universe's own intricate currency. You can't have less than one of these fundamental units. This groundbreaking discovery, which was initially sparked by careful investigations into how light interacts with different types of matter, completely upended centuries of established physics. It provided the missing explanations for a host of phenomena that had puzzled scientists for ages. For example, it clarified why heated objects glow in very particular colors rather than a smooth spectrum. It explained why atoms absorb and release light only in very narrow, specific bands of color, almost like a unique fingerprint. And it revealed why energy can sometimes appear to jump in discrete steps, rather than flowing steadily and smoothly. Without this fundamental concept, known as quantization, much of our modern technology, from the precision beams of lasers to the microscopic components of the computers we use every day, simply wouldn't exist. This idea was the essential key that unlocked the very first doorway into the vast and mysterious realm of quantum theory itself. It sounds absolutely impossible, doesn't it? How can something be both a flowing wave and a solid, distinct particle at the same time? Yet, that's precisely how objects behave in the quantum domain. Take light, for instance. If you direct a beam of light through two extremely narrow slits, it doesn't produce a pattern of light and dark bands on a screen, just like water waves do when they pass through an opening. This is a classic sign of wave behavior. But here's the twist. If you then try to detect the light, not as a continuous wave, but as individual, tiny particles, each photon lands at a single, precise point, like a miniature bullet hitting a target. So, it acts like a particle. The truly astonishing thing is that this same dual behavior holds true for electrons, for entire atoms, and even for some molecules that are relatively large in the quantum sense. This wave-particle duality suggests something fundamental. Particles don't actually travel as fixed, tiny spheres. Instead, they exist as a kind of probability smear across space, spread out like a wave until the very moment they are observed. When that observation happens, their widespread, wave-like presence suddenly collapses into a single, definite location. This strange, two-faced identity isn't just a weird quirk of the quantum world. It's absolutely central to the whole framework of quantum mechanics. It means that what we commonly perceive as solid, distinct, and located in a single spot is actually part of a much larger, more fluid pattern. This pattern only sharpens and becomes concrete when we actively engage with it, when we actually look. It sounds almost like a magic trick, but simply observing something can fundamentally alter how reality unfolds at these tiny scales. In the quantum world, the act of looking isn't a neutral, passive process. The very act of taking a measurement of a particle can change its state. The double-slit experiment, which we just mentioned, provides the most famous illustration of this. When photons or electrons are left alone to travel through the slits, they create those wave-like interference patterns we discussed. But if you try to watch which slit each particle goes through, if you introduce an observer or a measuring device, their behavior instantly switches. They stop acting like waves and start behaving like individual particles, creating two distinct bands, as if they only went through one slit or the other. It's almost as if nature becomes aware of our gaze, though physicists usually explain this by pointing out the unavoidable interaction that occurs between the measuring equipment and the quantum system itself. Still, this raises truly profound questions. If every single measurement we make changes reality, then what exactly is reality before we measure it? Does the world truly exist in a fuzzy, undecided state, a blend of possibilities, until something or someone compels it to pick just one outcome? Whether you consider this a purely physical interaction or a deep philosophical puzzle, the idea that observation itself can change the outcome is one of the most astonishing and unsettling truths that quantum mechanics has revealed. It's a concept that has captivated and challenged scientists for more than 100 years. Nature, it turns out, has limits on how much we can ever truly know about a particle at any given moment. In the older, classical physics, the promise was clear. If you could just measure things precisely enough, you could know absolutely everything about a system. You'd know its exact position, its exact speed, and with that information, you could predict its entire future path with perfect certainty. Quantum mechanics, however, completely rewrites this promise. The Heisenberg uncertainty principle tells us that there are fundamental limitations to what we can simultaneously know. For example, the more precisely you manage to pin down a particle's exact location, the less accurately you can possibly know its momentum, which is essentially its mass times its velocity. And conversely, if you precisely measure its momentum, its position becomes incredibly blurry and ill-defined. This isn't a problem with our instruments being imperfect or our techniques not being good enough. It's a deep, inherent characteristic of nature itself. Particles simply do not possess exact, fixed values for certain pairs of properties simultaneously. This uncertainty is not just a gap in our knowledge. It is a real and unavoidable aspect of how the universe works at this scale. What this means is that at the quantum level, the future can never be predicted with perfect accuracy. All we can ever hope to do is calculate the probabilities of different outcomes. This fundamental shift in thinking, from absolute certainty to inherent probability, completely transformed science and challenged some of our deepest assumptions about how the universe operates, moving away from a purely deterministic view. A particle can actually exist in multiple states at the same time. This concept, called superposition, is one of the most peculiar ideas in quantum physics. It means that a tiny particle can simultaneously be in several different states or even several different locations at once. Imagine an electron that isn't just spinning in one direction, but simultaneously spinning both up and down. Or a photon of light that, in a sense, travels along multiple paths at the same time. These multiple states exist together in a delicate, balanced blend, which is mathematically described by something called a wave function. It's only when we perform a measurement that the particle chooses one specific outcome, and the superposition, this blend of possibilities, instantly disappears. This isn't just some wild theoretical idea. Experiments have confirmed it repeatedly. Quantum computers, for instance, actively use superposition to perform many calculations concurrently, giving them incredible potential power for certain types of problems. In our everyday lives, we never directly see superposition because it collapses the moment we interact with anything on a macroscopic scale. Yet, at the quantum level, this, both, at once, existence is the standard, a constant reminder that our familiar reality is just one specific version pulled from a swirling, intricate cloud of countless possibilities. Reality, it turns out, is constructed from probabilities, not from fixed certainties. In the quantum realm, absolutely nothing is guaranteed until it actually happens. A particle's exact location, its momentum, or its spin isn't decided beforehand. Instead, these properties are described by a set of probabilities. These probabilities are contained within the particle's wave function, which evolves smoothly and predictably until some interaction or measurement takes place. Only at that moment does a single outcome emerge, chosen seemingly at random from all the possible ones. This inherent probabilistic nature isn't because we lack information or because our understanding is incomplete. It's a fundamental aspect of how the universe operates. Even if we had perfect, complete knowledge of the wave function, we could still only predict the likelihoods of various outcomes, never a definite, guaranteed result. This idea was deeply unsettling for many early physicists, including Albert Einstein, who famously expressed his discomfort by saying, "God does not play dice with the universe." However, over a century of meticulous experiments has consistently shown that at the smallest scales, probability isn't a sign of ignorance. It is, in fact, the very essence of reality itself. How these possibilities transform into a single reality is still one of the biggest unresolved questions in physics. We understand that a quantum system can exist in many potential states simultaneously, and that a measurement somehow reduces these many possibilities down to just one definite outcome. But the precise mechanism of how this collapse actually occurs, or even if it's a truly physical event, remains a profound mystery. Some theories suggest that collapse is a real, physical process, perhaps triggered by the act of observation itself. Other interpretations propose that all possibilities actually happen, but we, as observers, simply experience one particular branch of a much larger, ever-splitting multiverse. Yet another viewpoint argues that collapse is merely an illusion, a convenient mathematical description, and that the wave function never truly reduces at all. Despite decades of intense debate and countless thought experiments, there's no widespread agreement or consensus on this fundamental issue. What we do know for sure is that this pivotal moment, this transition from many possibilities to one concrete reality, is absolutely central to our experience of the world. Fully understanding it might demand not just new physical theories, but perhaps an even deeper comprehension of the nature of consciousness itself and a re-evaluation of the very limits of what we can know. Schrödinger's cat, a famous thought experiment, is both alive and dead until someone looks inside the box. In 1935, the physicist Erwin Schrödinger came up with this imaginative scenario to highlight just how bizarre quantum superposition would be if it were applied to everyday objects. Imagine a cat placed inside a sealed box. Inside the box, there's a device with a single radioactive atom, along with a vial of poison. There's a 50-50 chance that the atom will decay within a certain time, and if it does, it triggers the release of the poison, which kills the cat. According to quantum theory, until the atom is observed, it exists in a superposition, a blend of both decayed and not decayed states. So, by extension, the cat, linked to this atom, is theoretically both alive and dead at the same time. It's only when you open the box and make an observation that this superposition collapses and the cat becomes definitively either alive or dead. Schrödinger didn't intend for us to take this literally for actual cats. His purpose was to illustrate the inherent absurdity of applying quantum rules to objects on our macroscopic scale. Yet, his famous cat remains one of the clearest and most enduring ways to visualize the deeply strange and counterintuitive nature of quantum mechanics. Two particles can truly share a single existence, even when separated by vast distances. This phenomenon, known as entanglement, is one of the most baffling aspects of quantum mechanics. It's a state where two particles become so intricately linked that their individual properties are no longer independent. If you measure a property of one of these entangled particles, say its spin, the properties of the other particle instantly snap into a correlated state, no matter how far apart they are. It's as if they aren't really two separate particles at all, but rather a single, unified system stretched across space. This profound connection doesn't weaken with distance. It also doesn't rely on any signals traveling between them in the conventional sense, because that would imply a speed limit. Once entangled, these particles share a kind of joint identity, a shared destiny. Scientists have successfully created entanglement in laboratories using various particles, like photons, electrons, and even small groups of atoms. It's a very fragile link, easily broken by outside interference or interaction with the environment. However, when it's carefully preserved, it hints at a much deeper layer of reality, one where the idea of separation is merely an illusion, and the entire universe might be far more interconnected than we can ever directly perceive. If you touch one entangled particle here, another one, far away, responds immediately. Consider two particles that are entangled and then sent to opposite sides of the planet. Something truly extraordinary happens. If you measure a characteristic of one particle, that measurement instantly determines the corresponding characteristic of the other particle. This occurs even if they are so incredibly far apart that light, the fastest thing we know of in the universe, couldn't possibly carry a message between them in the time it takes for the effect to be observed. It's not that information is traveling faster than light in the conventional sense. Instead, it's more accurate to say that the two particles didn't have independent, predefined states to begin with. In a very deep sense, they are part of the same quantum entity. This instantaneous connection has been rigorously tested over and over in labs, with distances ranging from a few meters to hundreds of kilometers. The experimental results consistently align with the predictions of quantum theory. No matter how counterintuitive they might seem to our everyday understanding, it serves as a powerful reminder that our common notions of cause and effect, and even of distance itself, might not apply in the most fundamental workings of nature. Even Albert Einstein was deeply troubled by this quantum connection. The great physicist famously disliked the idea of entanglement, referring to it as spooky action at a distance. He was convinced that it must represent an incomplete description of reality. In his mind, there simply had to be hidden variables, some unseen, underlying factors that could explain the strange correlations between entangled particles without having to invoke instantaneous, faster-than-light effects. Along with his colleagues Boris Podolsky and Nathan Rosen, he formulated a thought experiment in 1935, now known as the EPR paradox, specifically to challenge the completeness of quantum mechanics. They argued that if quantum theory was truly correct, it would imply either impossible communication between distant particles or that particles didn't possess definite properties until they were measured. Both of these conclusions struck them as absurd. Ironically, decades later, experiments definitively proved that entanglement is real and cannot be explained away by hidden variables alone. Einstein's own profound challenge ultimately helped to inspire the very research that confirmed one of quantum mechanics' most mysterious features. Experiments have consistently shown that this connection is both real and, in a sense, unbreakable. For many decades, entanglement remained largely a theoretical curiosity, a strange prediction of quantum mathematics. Then, beginning in the 1970s, physicists started to design ingenious experiments to test it directly. They used pairs of photons, measuring the correlations between their properties and comparing these results with the predictions of quantum mechanics versus those of classical theories that relied on hidden variables. The outcomes were consistently decisive. Quantum mechanics won. Since those initial tests, the experiments have become increasingly precise, closing any potential loopholes and extending the distances over which entangled particles are observed. In a truly remarkable feat, in 2017, scientists successfully sent entangled photons between ground stations and a satellite orbiting Earth, confirming the effect over distances exceeding 1,000 kilometers. Each successive achievement only strengthens the conclusion. Entanglement isn't just a fragile oddity confined to carefully controlled laboratories. It's a fundamental property of reality. And as strange as it may seem, the universe permits this perfect, instantaneous connection to exist without any visible or conventional physical link whatsoever. There's no hidden mechanism that can fully explain these strange correlations. Einstein had hoped that the bizarre behavior of entangled particles could be accounted for by hidden variables, secret information somehow carried by the particles from the moment they were created, predetermining their future actions. However, in the 1960s, physicist John Bell developed a brilliant mathematical test specifically designed to determine whether such hidden variables could exist. His groundbreaking result, now known as Bell's theorem, demonstrated that if hidden variables were indeed real and local, the correlations between entangled particles would be limited in very specific ways. Quantum mechanics, however, predicted much stronger correlations, and experiments have consistently confirmed these stronger quantum predictions. This means that no theory relying solely on local, hidden information can completely explain what's happening. The universe, at its most fundamental level, doesn't operate according to the neat, deterministic rules that Einstein had envisioned. Instead, it behaves in a way that suggests reality is more deeply connected and perhaps less local than we ever thought possible. Bell's theorem fundamentally proved that the universe doesn't behave in a classical way. This theorem is recognized as one of the most profound discoveries in all of physics. It doesn't merely state that quantum mechanics is peculiar. It asserts that if the theory's predictions are accurate and experiments confirm they are, then the universe itself cannot be fully described by any classical model that relies on local causes. The fact that experimental observations consistently match quantum predictions means that nature either permits instantaneous influences across vast distances, violating our normal understanding of locality, or it completely abandons the idea that objects possess definite properties before we actually measure them. Either way, it forces us to profoundly rethink what real means and how reality is fundamentally structured. Bell's work, which was once a specialized topic, has now become absolutely central to the field of quantum information science. It has laid the essential groundwork for developing advanced technologies like quantum cryptography, which ensures ultra-secure communication, all built upon the very spooky action that Einstein found so hard to accept. Quantum teleportation is a process that sends a particle's identity to another location, not the particle itself. This isn't the kind of teleportation you see in science fiction movies, where objects or people instantly vanish from one place and reappear somewhere else. Instead, quantum teleportation is about transferring the state or identity of one quantum particle to another, using entanglement as the essential bridge between them. Here's how it generally works. First, two particles are made to be entangled. One of these entangled particles is then sent to the desired destination, while the other remains with the sender. Next, a special combined measurement is performed on the sender's particle and the particle whose state is to be teleported. This measurement effectively destroys the original quantum state at the sender's location. But the precise quantum information is simultaneously recreated in the entangled particle at the destination. No physical matter actually travels between the 2 points, but the exact quantum information, the identity, of the original particle does effectively leap from one location to another. This process has been successfully demonstrated with photons, atoms, and even ions, over distances ranging from a few meters to hundreds of kilometers. It's a crucial ingredient for building future quantum networks. And while it won't beam humans across space, it accomplishes something equally astonishing. It allows the unique quantum blueprint of a system to instantly appear in a new spot. Some scientists now believe that spacetime itself might actually emerge from entanglement. In recent years, a truly bold and fascinating idea has gained increasing attention within the physics community: that the very fabric of spacetime, the stage upon which all cosmic events unfold, could be intricately woven from quantum entanglement. According to this perspective, the geometry of space, all the distances, the curves, and the connections between different points could simply be the large-scale manifestation of countless microscopic quantum links. If this theory proves to be true, it would imply that gravity, the force that shapes galaxies and keeps us grounded, and even the fundamental shape of the universe, aren't basic properties at all. Instead, they would be emergent phenomena arising from a deeper layer of quantum information. Theoretical research in areas like holographic duality and tensor networks offers hints about how such a connection might function. While still quite speculative, this idea has the potential to unify Einstein's general relativity with quantum mechanics into a single, cohesive framework. It suggests that without entanglement, space itself might literally unravel, dissolving into a collection of unconnected points. The universe, in its entirety, may be subtly woven together by countless quantum links. If entanglement is as pervasive and universal as quantum theory suggests, then it's not just a curious effect observed in the lab. It's happening everywhere, all the time, across the cosmos. Particles that were created together in the fiery hearts of distant stars, or those that originated in ancient cosmic events, or even those that sprang into existence during the Big Bang itself, might still be connected by these invisible, quantum threads. In this profound sense, the universe would be less like a vast collection of separate, independent objects and more like a single, seamless, interconnected whole. These quantum connections might weaken or decohere when disturbed by the environment, but new ones are constantly forming as particles interact with each other. The idea that reality is stitched together in this intricate way fundamentally challenges our traditional picture of the cosmos as a mostly empty expanse, dotted with isolated points of matter. Instead, it suggests that everything is part of one enormous, ongoing quantum conversation, silently written in the shared, fundamental language of entanglement. Entangled particles can sometimes maintain their deep bond against incredible odds. Entanglement is generally quite delicate. It can easily be disrupted and destroyed by factors like heat, unwanted noise, or interactions with the surrounding environment. This process is known as decoherence. Yet, under specific conditions, this quantum bond can persist in truly surprising ways. Certain exotic systems, such as superconductors and Bose-Einstein condensates, have the ability to hold vast numbers of particles in entangled states that endure for extended periods. Even beyond the controlled environment of a laboratory, traces of entanglement have been detected between particles separated by considerable distances in the messy, noisy, real world. This resilience makes entanglement not just a fragile scientific curiosity, but a potential, powerful resource for future technologies. If we can learn to better protect and control these quantum links, we could harness their enduring bonds to power revolutionary quantum communication networks, advanced quantum computers, and incredibly sensitive quantum sensors on a scale that could completely transform how we share and process information. Electrons, despite being considered infinitely small, still spread out like hazy clouds. The electron is one of the most familiar subatomic particles. It's the particle that flows through electrical wires, forms the crucial bonds that hold atoms together, and fundamentally shapes the chemistry that underpins all life. Yet, when scientists attempt to measure its size, they encounter something truly baffling. The electron behaves as if it possesses no internal structure, no discernible parts, and no measurable diameter. It appears to be a fundamental, point-like particle. At the same time, it doesn't act like a tiny, fixed pinpoint. Instead, its presence is smeared out, existing as a cloud of probability that surrounds the atomic nucleus. The specific patterns of this electron cloud are dictated by complex quantum rules. This cloud isn't a physical fog or mist. It's a dynamic map that shows where the electron is most likely to be found at any given moment. In one instant, it might be very close to the nucleus. In the next, it could be much further away. And, crucially, it's impossible to predict its exact location until you actually look for it. This dual nature, being both point-like and spread out, is a perfect illustration of how quantum particles consistently defy our common, everyday intuition. Weightless photons, the particles of light, can still exert a physical push on objects. Photons have no mass when they are at rest, which means they are truly weightless. However, they definitely carry both energy and momentum. This means that when a photon strikes an object, it can transfer a tiny bit of that momentum, exerting a pressure. This phenomenon is known as radiation pressure. In the vast emptiness of space, where there's no air to create resistance, this minuscule push can accumulate over long periods, leading to significant effects. Sunlight, for example, can subtly alter the paths of tiny dust grains, asteroids, and even spacecraft over time. Engineers have even taken advantage of this by designing solar sails, enormous, mirror-like sheets that capture the momentum from sunlight to propel spacecraft, completely eliminating the need for conventional fuel. On much smaller scales, precisely focused beams of light can be used to trap and manipulate microscopic objects, a technique called optical tweezers, which is an invaluable tool in fields like biology and nanotechnology. The fact that something as seemingly insubstantial as light, with no rest mass, can physically move matter is one of its most surprising and incredibly useful quantum properties. Billions of ghostly neutrinos pass through you every second, completely unnoticed. Every single moment, countless neutrinos are streaming right through your body without you feeling a thing. These incredibly tiny, nearly massless particles are produced in astonishing numbers by the sun, by distant stars, by violent supernova explosions, and even by the natural radioactive decay occurring within Earth's crust. Neutrinos interact so incredibly weakly with other matter that they can pass through entire planets, even entire galaxies, as if they were nothing more than empty space. Trillions upon trillions of them are flowing through Earth and through you at any given moment. Yet, because of their elusive nature, detecting them is extraordinarily difficult. Scientists build massive underground detectors, often filled with vast quantities of ultra-pure water or ice, patiently waiting for the incredibly rare event when a neutrino actually collides with an atom. Studying these elusive particles can unlock profound secrets about how stars function, how the universe evolved from its earliest moments, and even whether matter and antimatter are perfectly symmetrical, which is a major puzzle. Invisible, almost intangible, neutrinos are compelling proof that the cosmos is filled with an immense amount of hidden motion and energy that we barely perceive. Quarks, the fundamental building blocks of protons and neutrons, are forever trapped in groups of 2 or 3. Quarks are the tiny, fundamental constituents that make up protons and neutrons, and thus, most of the ordinary matter we observe around us. However, unlike electrons, which can exist independently, quarks are never found alone. They are perpetually confined within larger particles by the incredibly powerful strong nuclear force, which is mediated by other particles called gluons. This force behaves in a peculiar way. It actually grows stronger as you try to pull quarks apart, much like a very stiff rubber band that resists more and more the further it's stretched. If you try to separate quarks by adding a lot of energy, that energy doesn't free them. Instead, it creates new quark-antiquark pairs, which immediately bind together to form new particles. This phenomenon, known as quark confinement, means that quarks are permanently locked together, always appearing in combinations of 2s mesons or 3s baryons. It's as if nature has issued a decree: quarks can never be solitary travelers. They exist only as essential parts of a greater whole, forever bound within the very heart of every atom's nucleus. Gluons are responsible for the strongest bonds known in the universe. The strong nuclear force is the most powerful of the four fundamental forces of nature, and gluons are the particles that carry this incredible force. Their name comes from their crucial role in gluing quarks together to form protons, neutrons, and other composite particles. But gluons are unique among force-carrying particles, unlike the photons that carry the electromagnetic force or the hypothetical gravitons for gravity. Not only do gluons interact with quarks, but they also interact with each other, creating a dense, self-binding network that effectively traps quarks inside their composite particles. This self-interaction makes the strong force so incredibly intense that attempting to break a single proton apart would require energies far beyond anything we can generate on Earth, outside of specialized particle accelerators. Without gluons, atoms, and indeed all the matter they form, simply could not exist in a stable form. In a very real sense, gluons are the hidden, powerful threads that keep the entire universe stitched together at its absolute smallest scales. Without the Higgs boson, mass itself would not exist. The Higgs boson, a particle finally discovered in 2012 at CERN's Large Hadron Collider, was the last missing piece in the standard model of particle physics. Its existence is tied to the Higgs field, an invisible energy field that permeates all of space, extending throughout the entire universe. As various fundamental particles move through this omnipresent field, they interact with it, and this interaction is what gives them their mass. Think of it like walking through thick treacle. Some particles barely feel it and remain light, while others get bogged down and acquire significant mass. Without the Higgs field, particles like quarks and electrons would have no mass at all, and without mass, atoms couldn't form, planets couldn't coalesce, and life as we know it would be impossible. The Higgs boson itself is a tiny quantum ripple, a vibration, in this Higgs field, detectable only in extremely high energy collisions. Its discovery confirmed a theory that had been proposed decades earlier and led to a Nobel Prize for Francois Englert and Peter Higgs. More importantly, it provided a profound and fundamental answer to a seemingly simple question: why does anything in the universe weigh anything at all? Empty space is not truly empty. It constantly boils with fleeting virtual particles. Even in what we consider a perfect vacuum, a region utterly devoid of all matter and energy, space is not truly still and lifeless. Quantum field theory, our most successful description of particle physics, predicts that pairs of particles and their corresponding antiparticles are constantly flickering into existence. These virtual particles briefly borrow energy from the vacuum, existing for an incredibly short time before annihilating each other and disappearing back into the vacuum. These virtual particles cannot be directly observed or detected in the same way as real particles, but their effects are measurable. For instance, they cause tiny, subtle shifts in the energy levels of electrons within atoms. They also produce measurable forces between closely spaced objects in a vacuum, a phenomenon known as the Casimir effect. This constant, restless bubbling of activity means that empty space is far more like a turbulent, restless ocean than a calm, still void. The concept that nothing is actually full of these temporary, unseen particles is one of the most astonishing and thoroughly confirmed predictions of quantum physics. The quantum vacuum isn't just bustling with activity, it's bursting with energy. All those fleeting virtual particles constantly popping into and out of existence in the vacuum carry an inherent energy, often called zero-point energy. This energy exists even when a system is in its absolute lowest possible energy state, with no heat, no motion, and no light. It's a direct consequence of the Heisenberg uncertainty principle, which tells us you can't have a field with perfectly zero energy, because that would mean knowing both its precise position and its precise momentum simultaneously, which is forbidden. Zero-point energy is incredibly tiny on human scales. However, because it exists everywhere, permeating every cubic centimeter of space, it may add up to something truly enormous across the entire cosmos. In cosmology, some scientists propose that dark energy, the mysterious force causing the universe's accelerated expansion, might be directly linked to this vacuum energy. The immense paradox, though, is that theoretical calculations from quantum field theory predict a vacuum energy that is vastly, mind-bogglingly larger than what we actually observe as dark energy, by a factor of 10^120 in some estimates. This profound discrepancy suggests that we still don't fully understand one of the most fundamental ingredients of reality itself. Antimatter is like matter's perfect, but opposite, twin. For every known type of particle, there exists a corresponding antiparticle. These antiparticles have the same mass as their normal matter counterparts, but they carry opposite charges and other reversed properties. For example, the antiparticle of an electron, which has a negative charge, is a positron, which has a positive charge. When a particle encounters its antiparticle, they instantly annihilate each other in a brilliant burst of pure energy, converting their mass entirely into photons of light. Antimatter was first predicted by Paul Dirac in 1928 and was soon after discovered in cosmic rays. Today, it is exceedingly rare in the universe. Most of it was destroyed in mutual annihilations with matter shortly after the Big Bang. Why matter survived and antimatter largely vanished remains one of the great unsolved mysteries of physics. We can create antimatter in powerful particle accelerators and even manage to trap tiny quantities of it. However, storing it is incredibly challenging because it instantly annihilates upon contact with any ordinary matter. Antimatter isn't just a scientific curiosity. It has potential practical applications in medicine, such as in PET scans, and in theoretical future propulsion systems that could, in principle, harness its incredible energy density. Matter can be created directly from pure energy and then erased back into energy. Albert Einstein's most famous equation, E=mc², beautifully tells us that mass, matter, and energy are simply two different forms of the same fundamental entity. Under the right conditions, energy can indeed transform into matter, and matter can transform back into energy. For example, in extremely high-energy collisions, like those that occur in particle accelerators or in the violent environments near black holes, pure energy can spontaneously produce pairs of particles and antiparticles. Conversely, when a particle meets its antiparticle, they annihilate, converting their entire mass back into photons, which are packets of pure energy. This constant, dynamic interchange between mass and energy plays out continuously throughout the cosmos, in the nuclear furnaces at the hearts of stars, in the earliest moments of the universe's existence, and in extreme astrophysical events. It powerfully demonstrates that matter isn't a permanent, solid, unchanging substance. Instead, it's a form that energy can temporarily take, briefly shaped into particles before ultimately returning to the form of light. Every particle we observe is simply a ripple or a vibration in an invisible field that permeates everything. According to quantum field theory, our most comprehensive framework for describing particles and forces, the universe isn't just made of tiny, distinct particles floating around in empty space. Instead, it's composed of fundamental, underlying fields that stretch out everywhere, continuously filling all of space. Each type of particle is, in this view, nothing more than a localized vibration, an excitation, or a ripple in its own specific field. So, electrons are ripples in the electron field. Photons, the particles of light, are ripples in the electromagnetic field, and so on for every other type of particle. Even when there are no observable particles present, the fields themselves still exist, subtly quivering and filling all of space. This way of thinking elegantly unites matter and energy, showing them as different expressions, different dances, of the same underlying fabric of reality. It also fundamentally means that particles aren't tiny, indivisible marbles. They are more like events, temporary disturbances in something far deeper and more fundamental. Wherever you are right now, these invisible fields are present, quietly shaping everything you see, touch, and experience. Quantum field theory seamlessly merges particles and forces into a single, unified description. Before the advent of quantum field theory, particles were generally seen as distinct objects, and forces were thought of as separate, invisible influences that acted between them. However, QFT revealed a more profound connection. Forces themselves actually arise from fields, and their effects are carried or mediated by specific particles. For instance, in electromagnetism, the electromagnetic field generates photons, and these photons are the carriers of the force that acts between charged particles. Similarly, the powerful, strong nuclear force emerges from the gluon field, with gluons acting as its mediators. The weak nuclear force, responsible for radioactive decay, is mediated by the W and Z bosons. Even gravity, the most familiar force, may eventually be described in this way, though a complete quantum theory of gravity, incorporating its own mediating particle, the graviton, is still an elusive goal for physicists. Quantum field theory is one of the most successful and experimentally verified frameworks in all of science. With its predictions confirmed to extraordinary precision, it provides our best current description of reality at the smallest scales, offering a single, elegant language for both the matter that exists and the fundamental forces that cause it to move and interact. Even the emptiest space is incredibly alive with constant activity. If you picture the vacuum of space as a cold, utterly empty nothingness, quantum physics invites you to completely rethink that image. Even in the absence of any real particles, the underlying quantum fields are never perfectly still. They constantly quiver with tiny, inescapable fluctuations, which momentarily produce virtual particles that pop into existence and then vanish just as quickly. This restless, bustling background activity is present everywhere in the vast voids between stars, deep inside atoms, and even, imperceptibly, in the empty space of your living room. It represents a baseline energy that simply cannot be switched off or removed. And while most of this activity remains hidden from direct view, it leaves measurable fingerprints in various experiments. The profound realization that nothing is actually a seething, active medium completely changes our understanding of space itself. It's not a passive, inert stage upon which reality unfolds. Instead, space is an active participant, quietly shaping the cosmic drama at every single moment. A perfect vacuum can actually pull objects together. It sounds like something from a science fiction story, doesn't it? But if you place two uncharged, perfectly smooth metal plates very close together in a perfect vacuum, they will, in fact, slowly drift towards each other. This is called the Casimir effect, and it's a direct, measurable consequence of those quantum vacuum fluctuations we just discussed. The tiny gap between the plates acts like a boundary, allowing only certain wavelengths of virtual particles to exist within it, while the space outside the plates permits a wider range of wavelengths. This difference in the allowed quantum fluctuations creates a slight imbalance in pressure, effectively pushing the plates inward. The force generated by the Casimir effect is incredibly small, but it has been successfully measured in laboratories, providing compelling experimental confirmation that the vacuum is far from empty. Though it doesn't yet have widespread practical uses, the Casimir effect is a striking reminder that profound quantum forces can emerge from what we perceive as nothing, subtly shaping the motion of real, physical objects. Zero-point energy exists everywhere, permeating the entire universe. Even when a system is cooled to its absolute lowest possible energy state, devoid of all heat, motion, and light, it still contains an irreducible, residual amount of energy. This is known as zero-point energy. It's a direct and unavoidable consequence of the Heisenberg uncertainty principle. You simply cannot have a quantum field with absolutely zero energy, because that would imply knowing both its exact position and its exact momentum with perfect precision, which is fundamentally forbidden by nature. Zero-point energy is minuscule on human scales, but because it exists in every single cubic centimeter of space, it could potentially add up to something truly enormous across the entire cosmos. Some theories propose that this pervasive energy could be intimately linked to the mysterious dark energy, which we believe is driving the universe's accelerating expansion. Regardless of whether that specific link is ultimately proven, zero-point energy stands as one of the clearest and most compelling examples of how quantum physics tells us that empty space is never truly empty. Empty space, surprisingly, can actually warp gravity and time. In Albert Einstein's theory of general relativity, the presence of mass and energy dictates how space-time curves, and in turn, this curvature tells matter how to move. If the vacuum itself is filled with quantum energy, this pervasive zero-point energy, then even empty space can subtly influence the geometry of the universe. This means that quantum effects might subtly influence gravity and perhaps even the very flow of time. In principle, the density of this vacuum energy could alter how the universe expands, how galaxies form and cluster, and even how time itself passes in extreme conditions, such as near massive objects. The exact nature of this interaction is still a profound mystery, partly because successfully combining quantum theory and gravity into a single, unified framework remains one of the most challenging problems in all of physics. However, it's entirely possible that the key to understanding the grand evolution of the cosmos lies hidden within the intricate, active structure of empty space itself. Powerful fields have the ability to twist and change the very nature of the vacuum. The quantum vacuum might feel like an unchangeable, immutable background, but under extreme conditions, it can actually transform. Very strong electric or magnetic fields can polarize the vacuum. This means they can align its virtual particles in specific ways, which subtly alters the vacuum's properties. In theory, if these fields were intense enough, they could even cause the vacuum to essentially break down, leading to the spontaneous creation of real particle-antiparticle pairs directly from the vacuum's energy. This remarkable phenomenon, known as vacuum decay, has not yet been observed directly in experiments. The strength of the fields required to trigger it are currently far beyond anything we can generate in our laboratories. However, its effects are precisely predicted by quantum electrodynamics, one of our most successful theories. Such behavior indicates that the vacuum is not a passive, inert backdrop for events, but rather an active, dynamic medium that can respond to its environment in truly surprising and profound ways. Black holes, those famously inescapable cosmic giants, actually glow by subtly stealing energy from empty space. Black holes are renowned for their immense gravitational pull, so strong that nothing, not even light, can escape once it crosses the event horizon. Yet, quantum theory makes a remarkable prediction. Black holes are not perfectly black. They can slowly radiate energy away, a process known as Hawking radiation, named after the physicist Stephen Hawking. This happens close to the event horizon, where quantum vacuum fluctuations constantly create pairs of virtual particles. Normally, these particle-antiparticle pairs annihilate each other almost instantly. But at the very edge of a black hole, one particle from the pair might fall into the black hole while its partner manages to escape into space. To an observer outside the black hole, it appears as though the black hole itself is emitting a faint glow, slowly losing mass over an incredibly vast amount of time. This process is astonishingly faint for large, astrophysical black holes, making it nearly impossible to detect directly with current technology. Nevertheless, it represents a profound insight. Quantum physics suggests that even the darkest, most inescapable objects in the universe are not completely devoid of light and energy. The energy of nothingness itself might be actively driving the universe apart. In 1998, astronomers made a truly astonishing discovery. The expansion of our universe isn't just continuing, it's actually speeding up, accelerating. The precise cause of this cosmic acceleration remains one of the greatest mysteries in modern physics. But one of the leading candidates is a phenomenon called dark energy. This is a mysterious form of energy that appears to be intrinsic to space itself, built into its very fabric. If dark energy is indeed real, it behaves remarkably similarly to vacuum energy, exerting a constant outward pressure that pushes space apart. Over billions of years, this pervasive force could stretch the universe so far that distant galaxies would eventually slip entirely beyond our observable reach, effectively disappearing from our view forever. The profound idea that the ultimate fate of the entire cosmos might be determined by the subtle energy of empty space is one of the most haunting and thought-provoking results to emerge from modern physics and cosmology. The true nature of the quantum vacuum remains, at its core, unknown. We possess mathematical descriptions of the quantum vacuum, and we can measure its subtle effects in meticulously designed experiments. We can even draw connections between it and phenomena on cosmic scales, like the accelerating expansion of the universe. However, we still lack a complete, intuitive understanding of what the quantum vacuum truly is. Is it a physical medium, like some invisible, shimmering ocean that fills all of space? Is it simply a fundamental property of quantum fields that exist whether or not any particles are present within them? Or is it something even stranger, perhaps intimately tied to the very origin and fundamental structure of the universe itself? The quantum vacuum sits at a crucial intersection of quantum theory, general relativity, and cosmology, three foundational pillars of physics that, despite their individual successes, still resist full unification into a single, cohesive theory. Until we achieve a complete understanding of it, the emptiness between the stars will remain one of the most profound and mysterious aspects of reality, a silent enigma at the heart of everything. Quantum computers possess the remarkable ability to think in many realities simultaneously. Unlike traditional classical computers, which process information using binary bits that can only be in one of two states, either a 0 or a 1, quantum computers employ qubits. These are quantum bits, fundamental units of information that can exist in a superposition of both 0 and 1 at the same time. This extraordinary capability allows quantum computers to explore many possible solutions to a problem simultaneously. It's almost as if they are testing out outcomes across countless parallel realities before converging on a final answer. The computational power derived from this approach grows exponentially with each additional qubit, meaning that certain problems that would take even the fastest classical supercomputers millennia to solve could potentially be cracked by a quantum computer in mere seconds. While quantum computers are still in their very early stages of development, facing significant challenges with error correction and maintaining stability, they already offer a tantalizing glimpse into a future where complex problems in fields like chemistry, cryptography, and optimization could be solved with breathtaking speed and efficiency. It's not magic, it's the ingenious harnessing of quantum rules like probability and interference, applied in a way that classical logic could never hope to match. Qubits, the building blocks of quantum information, can effectively store multiple answers in a single moment. A qubit isn't confined to a single, definite state until the very moment it's measured. Before that observation, it can hold a delicate blend of possibilities, simultaneously representing both a 0 and a 1, each weighted by a specific probability. This unique property is precisely what gives quantum computers their immense potential power. With just a small number of qubits, you can represent an astronomical number of possible combinations at once. When a quantum algorithm runs, it meticulously manipulates these probabilities in a carefully choreographed way, ensuring that incorrect answers tend to cancel each other out through quantum interference, leaving the correct solution more prominent. It's akin to searching an entire vast library by examining all the books in parallel, rather than having to go through them one by one. The main challenge, however, is that any measurement causes a qubit superposition state to collapse into a single outcome. So, designing sophisticated algorithms that can extract useful results from this delicate, probabilistic blend is one of the central and most difficult tasks in the field of quantum computing. Entanglement isn't just a curious quantum phenomenon, it's a vital resource that supercharges quantum processing. In the context of quantum computing, entangled qubits share deep correlations that classical bits could never achieve. This allows operations performed on one qubit to instantly influence its entangled partners, no matter their physical separation. This interconnectedness enables quantum computers to perform incredibly complex computations far more efficiently than classical machines. It's as if distant parts of a problem can communicate and coordinate without physically transmitting information. Entanglement also plays a crucial role in quantum error correction, helping to detect and fix mistakes in fragile quantum states without directly observing and collapsing the qubits themselves. Without the powerful link of entanglement, quantum computers would lose much of their inherent advantage over classical systems. It acts as the invisible thread that binds their logic together, granting them the unique power to tackle problems that are utterly beyond the reach of even today's fastest supercomputers. Certain quantum algorithms have the potential to solve incredibly difficult problems in an instant. Some quantum algorithms are so remarkably efficient that, in principle, they could crack problems that would stump even the most powerful classical computers for centuries. A well-known example is Shor's algorithm, which can factor very large numbers exponentially faster than the best known classical methods. This is a groundbreaking achievement because the security of many of today's encryption systems, including those that protect online financial transactions, relies on the extreme difficulty of factoring large numbers. Another significant example is Grover's algorithm, which can dramatically speed up database searches in a way that no classical approach can match. It's important to note that these algorithms don't make quantum computers universally faster for every type of problem. However, for the specific classes of problems they are designed to address, the computational advantage can be truly enormous, transforming what is currently intractable into something solvable. This is precisely why governments, major technology companies, and research institutions worldwide are intensely racing to develop practical quantum processors. The first to successfully do so will unlock computational capabilities that could fundamentally reshape technology, security, and our understanding of the universe. Quantum cryptography is a revolutionary method that creates secrets that are fundamentally uncrackable. Traditional classical cryptography relies on the mathematical difficulty of certain problems, such as factoring large numbers. In theory, a sufficiently powerful computer, particularly a future quantum computer, could eventually break these codes. Quantum cryptography, however, takes a different approach. It leverages the fundamental laws of physics to guarantee absolute security. The most prominent method is quantum key distribution, or QKD. This technique involves sending encryption keys encoded in the quantum states of individual photons. The laws of quantum mechanics dictate that any attempt to eavesdrop on these photons, to observe or measure their state, will inevitably disturb them. This disturbance instantly reveals the intrusion to the legitimate users, making it impossible for an attacker to steal the key without being detected. This means that truly secure communication becomes possible even over channels that an attacker can fully monitor. Quantum cryptography has already been successfully tested in real-world networks, including satellite links, and could one day protect highly sensitive financial transactions, government communications, and personal data with a level of security that no classical system can ever hope to match. Quantum sensors are so sensitive, they can detect the barest whispers of change in the environment. By cleverly exploiting quantum effects like superposition and entanglement, quantum sensors can measure various physical quantities, such as time, acceleration, and incredibly subtle magnetic fields, with extraordinary, unprecedented precision. They are so remarkably sensitive that they can detect minute changes that would be completely imperceptible to any classical instrument. These include tiny shifts caused by gravitational variations, subtle electrical activity within the brain, or even the faint presence of elusive dark matter particles. Some advanced designs for these sensors utilize clouds of ultra-cold atoms or specially engineered nitrogen vacancy centers in diamonds to achieve this incredible sensitivity. In the future, quantum sensors have the potential to revolutionize fields like navigation, allowing for incredibly precise positioning without GPS signals. They could also transform medical imaging, offering new ways to visualize processes within the human body, and geological surveying, providing deeper insights into the Earth's subsurface. They promise to open entirely new windows into both the intricate workings of the human body and the deep structure of our planet. Superconductors allow electricity to flow indefinitely without any loss of energy. Normally, when an electric current travels through a conductor, it encounters resistance. This resistance causes some of the electrical energy to be converted into heat, resulting in energy loss. However, in certain unique materials, when they are cooled to extremely low temperatures, often just a few degrees above absolute zero, this electrical resistance completely disappears. This remarkable state is called superconductivity. In a superconductor, electrons pair up and flow coherently without encountering any resistance whatsoever, meaning the current can potentially circulate forever without losing any energy. This phenomenon is inherently quantum mechanical, relying on the collective behavior of countless particles acting together as a single, coherent quantum wave. Superconductors are already employed in many advanced technologies, such as the powerful magnets in MRI machines, the massive particle accelerators used in scientific research, and magnetic levitation trains. If scientists could achieve superconductivity at room temperature, it would trigger a technological revolution, transforming energy transmission by eliminating waste and enabling an entirely new generation of technologies. Quantum networks have the potential to connect quantum computers across the entire globe. Just as classical computers are interconnected by the vast global internet, future quantum computers could be linked together by quantum networks. These networks would utilize the principles of entanglement and quantum teleportation to transmit information in a way that is fundamentally impossible to intercept or copy without instantly being detected. Building such a network requires the challenging task of creating and maintaining entanglement over long distances. Researchers are already actively testing this using various methods, including optical fibers, satellite links, and specialized devices called quantum repeaters to extend the range. A fully functional quantum internet could enable ultra-secure communications, facilitate distributed quantum computing where multiple quantum machines work together, and open up new forms of sensing that operate across vast distances. Essentially, it could transform our entire planet into a single, interconnected quantum system. Atomic clocks are so incredibly accurate that they barely drift even over billions of years. The most precise timekeeping devices in the world are atomic clocks. These remarkable instruments utilize the incredibly stable, natural vibrations of atoms, often elements like cesium or ytterbium, as their precise ticks. In the most advanced versions of these clocks, atoms are cooled to temperatures very close to absolute zero and held meticulously in place by precisely tuned lasers. This allows their oscillations to be measured with an almost unimaginable level of accuracy. The very best atomic clocks are so stable that they would gain or lose less than a single second over the entire estimated age of the universe, which is nearly 14 billion years. This extreme precision isn't just an academic achievement, it's absolutely crucial for many modern technologies and scientific endeavors. It's essential for the accuracy of GPS navigation systems, for synchronized telecommunications networks, and for a wide range of fundamental scientific experiments that demand exquisite timing. Advances in quantum technology are pushing this accuracy even further, to the point where atomic clocks might soon be sensitive enough to detect minute changes in the passage of time, caused by tiny differences in gravitational potential, a prediction of Einstein's relativity. Quantum technology is already actively reshaping science and industry. While the futuristic potential of quantum computers often captures the headlines, quantum technology is not just a dream for tomorrow, it is already at work today in numerous areas of research and industrial application. Highly sensitive quantum sensors are being used to map underground structures, providing new insights into geology and resource exploration. Experimental quantum communication links are actively securing test networks, paving the way for unbreakable encryption. Quantum simulators, which are specialized quantum devices, are helping scientists model complex molecules and materials, offering new ways to understand their properties and design new substances. These tools are not theoretical science fiction. They are practical applications of quantum mechanics that are actively expanding our scientific and technological capabilities right now. As this technology continues to mature and become more robust, it is highly likely to profoundly influence a wide range of fields, from climate modeling and environmental science to drug discovery and advanced materials engineering, giving us completely new ways to understand and shape the world around us. The quantum revolution isn't something that's coming in the distant future. It's already here, quietly and profoundly changing the way we explore and interact with reality. The Copenhagen interpretation suggests that reality isn't truly real until it's measured. The Copenhagen interpretation, developed in the 1920s by pioneering physicists like Niels Bohr and Werner Heisenberg, remains one of the most widely taught and influential explanations of quantum mechanics. It posits that a quantum system doesn't actually possess definite, fixed properties until a measurement is performed on it. Before that crucial moment, it exists in a state of superposition, which is a blend of all its possible outcomes simultaneously. The act of measurement, according to this view, forces the system into one specific, definite state, causing its wave function to collapse. This interpretation is incredibly practical because its predictions perfectly match experimental results. However, it is also deeply unsettling philosophically. Does reality truly depend on observation to assume a definite form? Or is the collapse simply a convenient mathematical shortcut we use because we cannot possibly track every single quantum detail? The Copenhagen interpretation deliberately leaves these profound questions open, accepting uncertainty and fundamental unpredictability as an inherent part of the universe, rather than a flaw to be fixed or explained away. The many worlds view proposes that every possible outcome actually happens. Proposed by Hugh Everett III in 1957, the many worlds interpretation offers a radical way to circumvent the problem of wave function collapse entirely. Instead of a collapse, it suggests that when a quantum event has multiple possible outcomes, all of them actually occur, but they do so in separate, branching universes. So, if a particle has a 50-50 chance of going left or right, the universe, in this view, effectively splits. One new universe is created where the particle goes left, and another new universe branches off where it goes right. In this interpretation, reality is an ever-growing, infinitely complex tree of possibilities, with countless versions of ourselves living out every conceivable different history. While this interpretation elegantly preserves the mathematical equations of quantum mechanics without requiring any mysterious collapse, it raises truly staggering philosophical questions. If all possible outcomes genuinely happen, then what does it truly mean for us to make a choice? And could these supposedly parallel worlds ever interact or be observed by each other? It's a mind-bending idea that continues to spark intense debate. Pilot wave theory offers a different perspective, suggesting particles follow hidden paths. Also known as de Broglie, Bohm theory or Bohmian mechanics, pilot wave theory presents a more deterministic picture of the quantum world, aiming to remove some of the inherent randomness. It proposes that particles always have definite positions and velocities, unlike the indeterminate nature in standard quantum mechanics. These particles, however, are not moving randomly. They are guided by an underlying, invisible, pilot wave that evolves according to the Schrödinger equation. The strange wave-like interference patterns that we observe in experiments don't arise because particles are smeared out in space. Instead, they occur because this guiding pilot wave influences their precise trajectories. Pilot wave theory successfully reproduces all the predictions of standard quantum mechanics, but it does so by introducing hidden variables, unseen, underlying details that precisely determine how each particle moves. This is an appealing idea for those who are uncomfortable with the fundamental randomness of quantum mechanics. However, it requires accepting non-local effects, meaning that distant events can instantly influence each other, which is a concept that itself challenges our classical intuitions about cause and effect. Collapse theories propose that quantum states can end themselves spontaneously. These theories suggest that superpositions, those blends of multiple possibilities, don't necessarily last forever, even in the absence of an active measurement. Instead, they propose that quantum states eventually decay into a single, definite outcome on their own. In these models, quantum states evolve normally for a period, but there's a tiny, inherent chance per unit of time that they will spontaneously collapse. For very small systems, like individual atoms, this chance of spontaneous collapse is incredibly tiny, allowing superpositions to persist for a considerable time. However, for larger systems, which contain many particles, the cumulative chance of collapse becomes so high that it happens almost instantly, which is why we never observe macroscopic objects existing in visibly mixed quantum states in our everyday world. These theories aim to explain why we don't see quantum weirdness at human scales without needing to invoke conscious observers or the branching of parallel universes. Experiments are actively underway to test these collapse models by looking for faint, random bursts of energy that would signal a spontaneous reduction of the wave function, which could provide crucial evidence. Decoherence helps explain why quantum strangeness seems to disappear for larger objects. Decoherence isn't a completely separate interpretation of quantum mechanics, but rather a crucial physical process that helps us understand why quantum effects, like superposition and entanglement, appear to vanish in large systems. When a quantum system interacts with its surrounding environment, even with something as subtle as stray air molecules, random photons of light, or minute vibrations, information about its delicate quantum state subtly leaks away into the countless surrounding particles of the environment. This leakage of information effectively acts as a measurement of the system, even if we aren't consciously performing one. It destroys the delicate interference patterns of superposition and entanglement, causing the system to behave in a much more classical, predictable way. Decoherence happens incredibly rapidly for macroscopic objects, which is precisely why we never observe them existing in visibly mixed quantum states. While decoherence successfully explains the transition from quantum to classical behavior, it doesn't fully solve the deeper measurement problem. It still leaves open the fundamental question of how one specific outcome is ultimately chosen from the many possibilities. The measurement problem continues to puzzle even the most brilliant physicists. At the very core of quantum mechanics lies the profound measurement problems. How and why does a superposition, a blend of possibilities, become a single, definite outcome the moment it's observed? The mathematical equations of quantum mechanics beautifully describe the smooth evolution of a wave function over time, but they offer no explanation for the sudden, abrupt collapse into a definite state. Is this collapse a real, physical process that actually occurs in nature, or is it merely an apparent change in our knowledge about the system? Different interpretations, from the Copenhagen view to the many worlds hypothesis to various collapse theories, each offer distinct answers, but none have been definitively proven or universally accepted. The measurement problem is far more than an abstract theoretical puzzle. It touches directly upon the very nature of reality itself and raises fundamental questions about whether the world exists in a definite, concrete state even when no one is actively looking at it or measuring it. Could human awareness actually play a role in deciding reality's fate? Some interpretations of quantum mechanics, often considered quite controversial, suggest that consciousness itself might play a crucial role in collapsing the wave function. In this view, it's not simply the physical interaction with a measuring device that determines a specific outcome, but rather the as-awareness, or perception of an observer. This so-called observer effect is sometimes overstated in popular culture, leading to misconceptions. However, the underlying idea does have roots in serious discussions by influential physicists like John von Neumann and Eugene Wigner. While the majority of scientists today favor purely physical explanations for wave function collapse, the tantalizing possibility that the mind could somehow influence fundamental physical processes continues to intrigue. Testing this idea rigorously is incredibly difficult. But the profound question lingers: is reality, at least in part, shaped by our very act of noticing it? Quantum logic often defies our common sense. In classical logic, the kind we use every day, statements are definitively either true or false. There's no in between, no gray area. But in the quantum world, logic operates very differently. Properties of particles can be partly true and partly false simultaneously, depending entirely on the context of the measurement being made. Furthermore, the order in which you perform different measurements can actually change the outcome, something that simply never happens in classical physics, where measurements are assumed to be independent. Quantum logic reflects the deep, underlying mathematics of what's called Hilbert space, where events aren't simply yes or no, but rather probabilities that can subtly interfere with each other, much like waves. This fundamental departure from our everyday reasoning is a significant reason why quantum mechanics often feels so alien and counterintuitive. It's not just that the physical world behaves strangely at this scale, it's that the very rules we use to describe and understand it must be fundamentally rewritten. The universe, at its absolute core, might be fundamentally random. In quantum mechanics, some events appear to have no cause that can be predicted in advance, no matter how much information you possess. The spontaneous decay of a radioactive atom, for example, or the exact outcome of a particle measurement. These are described as fundamentally probabilistic events. This isn't randomness that stems from our ignorance, meaning we just don't know enough to predict it. Instead, it's randomness that is intrinsically built into the very fabric of reality itself. For some, this idea can be deeply unsettling, suggesting that the universe isn't a perfectly predictable, clockwork machine, but rather an unpredictable game of chance. For others, it's a liberating concept, allowing for genuine novelty, creativity, and unpredictability, even within a world governed by precise physical laws. Whether randomness is truly fundamental or merely a reflection of deeper physics that we haven't yet discovered remains one of the most profound and open questions in all of science. Quantum physics may even bend the very rules of space and time. At the most extreme scales, where the incredibly small meets the incredibly fast and dense, quantum mechanics and Einstein's theory of relativity begin to clash, and the results suggest that space and time themselves might not be as fixed and absolute as we intuitively believe. Quantum fluctuations, those constant jitters of virtual particles, can ripple through space-time, potentially creating tiny, temporary distortions in its fabric. Some ambitious theories of quantum gravity propose that space-time isn't continuous at all, but instead made of discrete, indivisible units, much like pixels on a cosmic screen. This smallest possible unit of length is known as the Planck length. Other theories suggest that time itself might not be a fundamental entity, but rather an emergent property that arises from deeper, timeless quantum laws. In experiments involving entangled particles, correlations have been observed that appear to transcend the normal limits of distance and time, hinting at profound connections that lie completely outside our familiar framework. If these radical ideas turn out to be correct, then space and time are not just the fixed stage upon which reality unfolds. They are integral parts of the cast, actively shaped by the same strange rules that govern the quantum world itself. Superfluid helium exhibits a truly bizarre behavior. It can flow up walls without any resistance. When helium gas is cooled down to an incredibly low temperature, just about 2 degrees above absolute zero, it undergoes a remarkable transformation. It enters a unique state of matter called a superfluid. In this extraordinary state, it completely loses all viscosity. Viscosity is the internal friction that normally slows down the flow of any liquid, making honey thick and water thin. As a result, superfluid helium can do things that seem utterly impossible. It can creep up and over the sides of a container, flowing against gravity in a thin, invisible film. It can pass effortlessly through pores so tiny they would block any ordinary liquid. And, once set in motion, it can circulate endlessly in a closed loop without ever slowing down or losing energy. This strange, macroscopic behavior arises directly from quantum mechanics operating on a large scale. All the helium atoms in a superfluid fall into the exact same quantum state, moving together as one perfectly coordinated, coherent wave. Superfluid helium provides a powerful demonstration that quantum effects, which we usually associate with the microscopic world of particles, can sometimes spill over and manifest in forms that we can directly see and touch in our everyday reality. Bose-Einstein condensates behave like a single, giant atom. These exotic states of matter, known as Bose-Einstein condensates (BECs), were first predicted in the 1920s by physicists Satyendra Nath Bose and Albert Einstein. They are formed when certain types of atoms, called bosons, are cooled to an astonishingly low temperature, just a tiny fraction of a degree above absolute zero. At this extremely cold temperature, the individual wave functions of the atoms begin to overlap and merge, creating a single, unified quantum state that extends across the entire sample of atoms. In essence, the entire condensate starts to behave as if it were one single, super, atom, with all its constituent particles moving in perfect, synchronized harmony. BECs provide scientists with an invaluable tool to study quantum phenomena on a scale large enough to observe directly, such as intricate interference patterns and the bizarre superfluid behavior. Their existence is a vivid and compelling reminder that matter can take on forms utterly unlike the familiar solids, liquids, and gases that we encounter in our daily lives. The quantum Hall effect gives rise to entirely new forms of matter. When electrons are confined to an ultra-thin layer of material, cooled to temperatures near absolute zero, and subjected to a very strong magnetic field, they can exhibit a truly remarkable phenomenon known as the quantum Hall effect. In this exotic state, the electrical resistance of the material takes on incredibly precise, quantized values. These values are exact fractions or integers of fundamental constants, and they remain astonishingly stable even if the material contains impurities or defects. This effect arises from the electrons organizing themselves into entirely new, collective quantum states. In some cases, their behavior cannot even be explained by ordinary particles at all, but rather by quasiparticles that appear to carry fractions of an electron's charge. The quantum Hall effect has significantly deepened our understanding of quantum mechanics, the mathematical field of topology, and condensed matter physics. It also holds considerable potential for practical applications, such as creating ultra-precise standards for electrical resistance and for developing stable components in future quantum computers. Topological materials host quantum states that are incredibly robust and cannot be easily destroyed. Topological materials are a fascinating class of substances whose electronic properties are not just determined by their chemical composition, but fundamentally by the shape of their quantum states in an abstract mathematical space. One of their most intriguing characteristics is the presence of special surface or edge states that are remarkably resistant to disturbance. These unique states can conduct electricity with almost no scattering, meaning electrons flow freely even in the presence of impurities or defects in the material. In some cases, these states are protected by the material's underlying topology in such a way that they simply cannot be removed or altered unless the material's fundamental, global structure is physically changed. These incredibly robust properties make topological materials highly promising candidates for creating stable quantum bits, or qubits, which could resist the noise and errors that currently plague and limit today's nascent quantum computers, bringing us closer to practical quantum computing. Quantum tunneling allows particles to pass directly through solid barriers. In the familiar world of classical physics, if a particle doesn't possess enough energy to climb over a barrier, it simply cannot get to the other side. It's like a ball rolling towards a hill that's too high. It will just roll back down. However, in the peculiar world of quantum mechanics, there's always a non-zero probability that a particle can tunnel right through a solid barrier, appearing on the other side without ever actually going over it. This happens because particles are described by wave functions, which have a non-zero probability of extending into and even beyond barriers, giving the particle a small but real chance of being found on the far side. Quantum tunneling is a crucial process in many natural phenomena, from the nuclear fusion reactions that power stars to the precise operation of tunnel diodes in modern electronics. It also places fundamental limits on how small we can make certain technologies. For example, in advanced microchips, electrons can sometimes tunnel through insulating barriers that are so incredibly thin that they cause unwanted leakage currents, posing a challenge for miniaturization. Stars shine brightly because quantum tunneling makes nuclear fusion possible. The core of our Sun, and indeed the cores of all stars, are surprisingly cooler than the temperatures that would theoretically be required for hydrogen nuclei to overcome their mutual electric repulsion and fuse together. According to classical physics, fusion simply shouldn't happen there at all because the nuclei don't have enough kinetic energy to get close enough. But quantum tunneling provides a crucial workaround. It allows atomic nuclei to slip through their mutual electrical repulsion and come close enough for the incredibly powerful strong nuclear force to bind them together. This fusion process releases the immense energy that powers the Sun, causing it to shine and providing the light and heat essential for life on Earth. Without quantum tunneling, the universe would be a much colder, darker, and ultimately lifeless place. Tunneling ensures that fusion can occur at the much lower temperatures and pressures found in stellar cores, making it a fundamental enabler of starlight and, by extension, of all life. Josephson junctions are devices that turn subtle quantum effects into usable electrical circuits. A Josephson junction is a special electronic component created by placing an extremely thin insulating barrier, typically just a few nanometers thick, between two superconducting materials. Due to quantum tunneling, pairs of electrons, known as Cooper pairs, can actually cross this insulating barrier without any applied voltage, creating a supercurrent that flows without resistance. This supercurrent can oscillate at incredibly precise frequencies when exposed to even a tiny voltage, making Josephson junctions invaluable in extremely sensitive applications. These include ultra-sensitive magnetometers called SQ-IDs, superconducting quantum interference devices, and the creation of highly accurate voltage standards. They are also absolutely central components in many quantum computers, where they form the fundamental building blocks of superconducting qubits. Josephson junctions serve as a clear and compelling example of how subtle quantum effects, when carefully controlled and engineered, can be transformed into incredibly practical and powerful tools for precise measurement and advanced computation. Continuously observing a system can effectively freeze its motion. This fascinating phenomenon is known as the quantum Zeno effect. It occurs when very frequent measurements prevent a quantum system from evolving or changing its state. In quantum mechanics, as we've discussed, the act of measurement causes a system to collapse into a definite state. If you measure the system often enough, so frequently that it doesn't have time to evolve away from its initial state, you can continuously reset it before it has a chance to change. This effectively freezes its behavior, preventing it from undergoing predicted quantum transitions or decay. This peculiar effect has been successfully demonstrated in experiments involving atoms and photons, and it holds potential applications in controlling delicate quantum states for use in quantum computing or secure communication. The quantum Zeno effect turns our intuitive understanding of observation completely on its head. Instead of merely revealing an existing reality, observation can, in this quantum context, actively shape and even halt the evolution of reality itself. Quantum levitation allows objects to float stably above magnets. By utilizing superconductors cooled below their critical temperature, it's possible to achieve the remarkable feat of making objects levitate stably above magnets. This phenomenon happens due to two key quantum effects. First, superconductors completely expel magnetic fields from their interior, a property known as the Meissner effect. Second, they can also pin magnetic field lines in place, effectively trapping them. The combination of these effects results in a stable, locked position in space, where the superconductor hovers either above or below a magnet, resisting any attempts to push it away or pull it down. Quantum levitation has been vividly demonstrated in various experiments showcasing frictionless motion. While it's not yet a common sight in everyday transportation, it offers a tantalizing glimpse into a future where vehicles could glide effortlessly without physical contact, powered by these incredible quantum effects. Some living organisms may actually use quantum tricks to survive and thrive. Growing evidence suggests that certain biological processes, even within living organisms, might exploit sophisticated quantum phenomena. In photosynthesis, for example, the tiny packets of energy, or excitations, created when sunlight is absorbed by plant cells, appear to travel through the plant's molecular structures using quantum coherence. This means they explore multiple possible paths simultaneously to find the most efficient route for energy transfer. Some species of migratory birds may even use quantum entanglement in light, sensitive proteins within their eyes to detect Earth's subtle magnetic field, allowing them to navigate with incredible precision. Even our sense of smell has been proposed to involve quantum tunneling, where electrons tunnel through barriers in receptor molecules, triggering a scent recognition. While these fascinating ideas are still actively being investigated and debated within the scientific community, they strongly suggest that nature itself may have been subtly harnessing and optimizing quantum effects for survival and function long before humans ever learned to describe them mathematically. The early universe, in its very first moments, was profoundly shaped by tiny quantum fluctuations. In the unimaginable first fractions of a second immediately following the Big Bang, the universe was incredibly small, unbelievably hot, and extraordinarily dense. It was a turbulent, seething quantum field where energy and matter were constantly flickering into and out of existence. During this chaotic epoch, tiny quantum fluctuations in density, arising directly from the Heisenberg uncertainty principle, rippled through this nascent cosmos. These fluctuations were microscopic in scale, barely perceptible at the time. However, as the universe rapidly expanded during a period known as cosmic inflation, these minute quantum ripples were stretched and amplified to cosmic scales, becoming enormous. Billions of years later, we can still observe their faint, subtle imprint in the cosmic microwave background radiation, the lingering afterglow of the Big Bang. These initial fluctuations acted as the crucial seeds, from which all the large-scale structure in the universe eventually grew the vast clusters of galaxies, individual stars, planets, and ultimately, life itself. Without this inherent quantum noise in the very beginning, the universe might have remained perfectly smooth, uniform, and utterly lifeless. Those initial quantum fluctuations eventually grew into all the galaxies we observe today. Once the early universe had cooled down sufficiently for gravity to begin to exert its influence. The slightly denser regions that were created by those initial quantum fluctuations started to attract even more matter. Over vast stretches of millions and hundreds of millions of years, these slightly denser regions slowly grew into immense clouds of gas. These massive clouds, in turn, eventually collapsed under their own overwhelming gravity to form the very first stars and then the first galaxies. The intricate distribution of galaxies that we see across the universe today, not randomly scattered, but instead clustered into enormous filaments, sheets, and voids, can be traced directly back to those minute quantum ripples that occurred in the universe's infancy. In a profound sense, every single galaxy glittering in the night sky, including our own Milky Way, is a magnificent, magnified shadow of a quantum event that unfolded nearly 14 billion years ago, a tiny fluctuation that grew to shape the entire cosmos. Black holes, despite their immense classical gravity, also have to follow the rules of quantum mechanics. We often think of black holes as being the exclusive domain of Albert Einstein's general relativity, where gravity reigns supreme and dictates everything. However, black holes, like all other entities in the universe, must also obey the fundamental laws of quantum mechanics. This becomes particularly important and complex at their very edges, the event horizon, where the extreme intensity of gravity directly encounters the strange realm of quantum fields. Effects like Hawking radiation, which describes how black holes slowly emit particles and evaporate, are purely quantum in nature and cannot be explained by classical physics alone. Fully understanding black holes requires successfully merging quantum mechanics with general relativity, a monumental scientific endeavor that physicists are still actively working towards. Studying these enigmatic cosmic objects could reveal entirely new physics, demonstrating how the smallest scale rules governing particles connect with the largest scale structure of spacetime itself. Inflation theory, which explains the universe's rapid early growth, was born from quantum principles. Cosmic inflation is a groundbreaking idea that proposes the universe underwent an incredibly brief, explosive period of expansion in its earliest moments, growing at a rate far exceeding the speed of light. This theory elegantly explains several perplexing features of the cosmos, such as why it appears so remarkably uniform and flat on large scales, while simultaneously allowing for very tiny, subtle variations within that uniformity. Those crucial initial variations actually originated from quantum fluctuations within the unflattened field itself, the hypothetical field thought to drive inflation. These microscopic quantum jitters were then stretched across vast distances by the incredibly rapid expansion of space during the inflationary epoch. Without the principles of quantum mechanics, the theory of inflation would be a very different story, or perhaps might not have emerged at all. The sophisticated combination of quantum randomness and this period of incredibly rapid growth provided the universe with its initial blueprint, a cosmic seed for all the structure and complexity we observe today. Dark energy, the mysterious force accelerating cosmic expansion, could indeed be the energy of the quantum vacuum. In 1998, astronomers made the astonishing discovery that the expansion of the universe is not only happening, but is actually speeding up. This acceleration is driven by some unknown entity we've termed dark energy. One of the leading hypotheses for the nature of dark energy is that it is simply the energy of the quantum vacuum itself, the background energy that fundamentally exists even in empty space. Quantum field theory strongly predicts that vacuum energy should exist. However, the amount it predicts is astronomically larger than what we actually observe as dark energy, creating one of the most significant and perplexing puzzles in modern physics, a discrepancy of 120 orders of magnitude. If dark energy truly is vacuum energy, then quantum mechanics isn't just shaping the tiny world of particles, but is fundamentally steering the ultimate fate and evolution of the entire cosmos on its grandest scales. Space itself might actually be made up of tiny, discrete units. In our everyday experience, space feels perfectly continuous. You can imagine moving any tiny distance you like, dividing it infinitely. But some advanced theories of quantum gravity propose that at an incredibly fundamental scale, known as the Planck scale, space might not be continuous at all. Instead, it could be composed of indivisible, discrete grains, which would be the smallest possible units of length. This concept is analogous to how matter appears smooth on large scales, but is fundamentally made of atoms underneath. If this idea is true, it would mean that space and time are not the ultimate, basic fabric of reality. Rather, they would be emergent properties, built up from even deeper quantum building blocks, much like a digital image is built from pixels. Directly detecting this fundamental granularity is currently far beyond our technological capabilities. However, it might leave subtle, detectable fingerprints in the way extremely high energy particles travel across the vast distances of the universe, offering clues about its deepest structure. The entire universe could be thought of as one vast, unified quantum object. If everything in the cosmos is interconnected through the intricate web of quantum entanglement, then, in a very profound sense, the entire universe might actually be a single, enormous, unified quantum system. This bold idea fundamentally challenges the traditional classical view of the cosmos as merely a collection of independent, separate parts interacting with each other. Instead, it suggests that every particle, every field, and every force could be part of one immense, entangled whole. This concept is certainly speculative, but it aligns with hints and observations from cosmology, particularly where correlations between widely separated regions of space seem almost too precise to have arisen purely by chance, suggesting some deeper, underlying connection. If this vision of a quantum universe is correct, then reality might be far more cohesive and fundamentally stranger than we have ever imagined, a single, intricate dance of interconnected possibilities. Quantum gravity is the ambitious scientific quest to unite all of physics. One of the greatest and most challenging goals in all of science is to successfully reconcile quantum mechanics with Albert Einstein's general relativity. These are the two monumental theories that currently describe vastly different realms of nature. Quantum mechanics for the incredibly small world of subatomic particles, and general relativity for the incredibly large world of massive celestial objects and the structure of spacetime. Quantum gravity seeks to merge these two powerful frameworks into a single, consistent, overarching theory that works seamlessly for both the microscopic and the macroscopic domains. Various approaches, such as string theory, loop quantum gravity, and holographic duality, are all leading contenders in this quest. However, a definitive, final answer has not yet been found. A successful theory of quantum gravity would not only explain what truly happens at the heart of black holes and at the very beginning of the universe, but it might also unveil the true, fundamental nature of space and time themselves. Wormholes, those intriguing hypothetical tunnels, might actually be entanglement made physical. Wormholes, which are theoretical shortcuts connecting distant points in space-time, have long been a staple of science fiction, capturing our imaginations. But some physicists are now proposing a truly mind-bending idea that these cosmic tunnels could actually be the geometric manifestation of quantum entanglement. In this fascinating concept, often summarized as ER-TUD-EPR, referring to Einstein-Rosen bridges, which are a type of wormhole, and Einstein-Podolsky-Rosen entanglement. Every entangled pair of particles could be thought of as being connected by a tiny, perhaps non-traversable wormhole. If scaled up to the cosmic level, this could mean that the very structure of spacetime is woven from countless quantum links, with wormholes acting as their visible, macroscopic shape. While still highly speculative and a subject of intense theoretical research, this concept offers a striking and elegant bridge between quantum theory and general relativity, suggesting that the fundamental fabric of the universe might literally be woven from the invisible threads of entanglement. Quantum physics holds the potential to be the ultimate key to understanding everything. Quantum mechanics already provides the foundational explanations for the behavior of particles, atoms, and molecules, which are the fundamental building blocks of chemistry and biology. It underlies the stable structure of all matter, dictates the intricate flow of energy, drives the life cycles of stars, seeds the formation of galaxies, and might even determine the universe's ultimate fate. Yet, despite its enormous success and explanatory power, quantum mechanics still leaves us with profound, unresolved mysteries. These range from the nature of measurement and the collapse of the wave function to its ultimate unification with gravity. Some physicists believe that a deeper, more complete understanding of quantum theory could unlock answers to questions that span all of science, from why the universe exists at all to whether its fundamental properties could have been different. In this ambitious view, quantum physics isn't just one important part of the vast scientific puzzle. It may, in fact, be the very frame that holds the entire puzzle together. Reality itself actually breaks its own rules at the smallest possible scales. The familiar, dependable rules of physics. The ones that keep planets gracefully orbiting their stars. The ones that ensure apples fall consistently from trees. These rules start to twist and contort in truly strange ways when you shrink your perspective down to the tiniest scales of nature. At the incredibly small level of atoms and the subatomic particles that compose them, matter can abruptly behave like a solid, localized object in one moment, and then like a diffuse, spreading wave the very next. Objects can exist in more than one state simultaneously, defying our expectation of distinct options. And crucially, outcomes are dictated by probabilities, by likelihoods, rather than by the absolute certainties we take for granted in our macroscopic world. Even the simple act of observing something at this level can fundamentally alter what's being observed. This isn't just some obscure, odd corner of physics, relevant only to specialists. This is the absolute foundation upon which everything else in the universe rests. The profound revelation that reality operates by one set of clear rules on its surface, and an entirely different, much stranger set underneath, is arguably one of the greatest scientific discoveries and intellectual challenges of the past century. Observing a quantum system inevitably changes its behavior. In the quantum world, the act of measurement is never a passive process. When you observe a quantum system, whether you're trying to pinpoint the exact position of an electron or track the precise path of a photon, the very interaction required to make that observation, shining light, applying a field, colliding with another particle, inevitably changes the system itself. This is most famously and strikingly demonstrated, once again, in the double-slit experiment. In this experiment, particles form those wave-like interference patterns when they are left unobserved, indicating they are exploring multiple paths. But the moment a detector is placed to observe which slit they pass through, they instantly switch to behaving like individual particles, creating two distinct bands. The difference isn't due to some intrinsic change in the particles themselves, but rather the fact that the measurement forces them out of their indeterminate quantum state and into a single, definite classical state. In quantum mechanics, to look is fundamentally to touch, and to touch is to change. The Heisenberg uncertainty principle fundamentally limits what we can ever truly know. Werner Heisenberg's profound uncertainty principle tells us that there are certain pairs of properties, such as a particle's position and its momentum, that cannot both be known with perfect, absolute accuracy at the same time. The more precisely you manage to measure one of these properties, the less precisely you can possibly know the other. This isn't because our measuring tools are somehow flawed or not advanced enough. It's a deep, inherent principle of nature itself. The universe simply does not allow both values to exist with perfect exactitude simultaneously. The uncertainty principle places a hard, fundamental limit on our knowledge, revealing that at the quantum level, reality is not as sharply defined and concrete as it appears to us in our everyday lives. Instead, it exists as a range of potential possibilities until some interaction or measurement forces it to narrow down to a more specific state. Wave functions are mathematical descriptions that contain the probabilities of all possible outcomes. In the realm of quantum mechanics, the complete state of any system is described by its wave function. This is a complex mathematical object that doesn't tell you exactly what will happen. Instead, it encodes all possible outcomes of a potential measurement and, crucially, the precise probabilities associated with each of those outcomes. Before a measurement is made, the system, in a sense, occupies all of these possible states simultaneously, each weighted by its probability. When a measurement then occurs, the wave function appears to collapse into a single, definite outcome, and all other possibilities vanish. This fundamentally probabilistic nature is one of the defining characteristics of quantum theory, dramatically replacing the clockwork certainty and deterministic predictions of classical physics with a softer, more flexible, and inherently uncertain reality. The collapse of a wave function remains a deep, unresolved mystery for physicists. Scientists can mathematically describe the phenomenon of wave function collapse with great precision, but they still cannot fully explain what physically causes it to happen, or indeed, whether it even truly occurs as a sudden, discrete event. In the widely accepted standard interpretation, the act of measurement forces a quantum system from its superposition of possibilities into a single, definite state. However, other interpretations offer completely different perspectives. Some suggest that the wave function never actually collapses, but rather that all possible outcomes happen in parallel, branching universes. Other, collapse models, propose that certain intrinsic processes or scales within nature naturally trigger the collapse without any need for conscious observation. Despite more than a century of intense debate and rigorous experimentation, no one has yet definitively solved this profound puzzle. The precise nature of wave function collapse remains one of the most intriguing and central open questions in all of physics, hinting at deeper layers of reality we have yet to fully comprehend. Quantum systems have the astonishing ability to exist in multiple states at once. The principle of superposition is what allows a quantum system to occupy more than one state simultaneously. This means an electron can exist in multiple locations at the same time. A photon can effectively travel along more than one path at once, and an atom can simultaneously exist in different energy levels. This isn't just abstract theory, it has been repeatedly confirmed in countless meticulous experiments. The key, however, is that these superpositions are incredibly delicate. They are easily disrupted and collapse into a single state the moment they interact with their surrounding environment. In the development of quantum computers, engineers are cleverly exploiting superposition to perform many calculations in parallel, which vastly increases the potential processing power for certain types of problems. In nature, superposition serves as a quiet, constant reminder that reality doesn't have to commit to a single option until it is absolutely forced to do so. Particles can become deeply linked world of particles, but it's fundamentally steering the ultimate fate and grand evolution of the entire cosmos itself. Space itself might actually be made of incredibly tiny, discrete units like pixels. In our everyday experience, space feels perfectly continuous. You can imagine moving any infinitesimally small distance you like, without hitting any sort of fundamental boundary. However, some advanced theories of quantum gravity propose a radical idea that at the Planck scale, an unimaginably tiny scale of length, space might not be continuous at all. Instead, it could be composed of indivisible, fundamental grains, representing the absolute smallest possible units of length. This would be analogous to how matter, which appears smooth on large scales, is fundamentally made up of discrete atoms underneath. If this theory proves correct, it would mean that space and time, which we perceive as the basic fabric of reality, are not actually fundamental entities themselves. Instead, they would be emergent properties built up from deeper, more fundamental quantum building blocks. Directly detecting this proposed granularity of space is currently far beyond our technological capabilities. However, it might leave subtle, detectable fingerprints in the way extremely high-energy particles travel across the vast distances of the universe, offering a tantalizing clue. The entire universe could, in a profound sense, be one vast quantum object. If every single particle in the cosmos is interconnected through the intricate web of quantum entanglement, then, in a very deep and meaningful way, the entire universe might be considered a single, unified quantum system. This bold idea fundamentally challenges the classical view of the cosmos as merely a collection of independent, separate parts. Instead, it suggests that every particle, every field, and every force could be part of one immense, intricately entangled whole. This concept is, of course, highly speculative, but it aligns with subtle hints from cosmology. For instance, correlations observed between widely separated regions of space sometimes appear almost too precise to have arisen purely by chance, suggesting some deeper, underlying connection. If this turns out to be true, the quantum universe might be far more cohesive, far more interconnected, and ultimately far stranger than we can currently imagine, operating with a unity that defies our everyday understanding of separation. Quantum gravity represents the ultimate goal to unite all of physics. One of the greatest and most ambitious goals in all of science is the monumental task of reconciling quantum mechanics with Albert Einstein's theory of general relativity. These are the two great foundational theories that currently describe different, yet equally crucial, realms of nature. Quantum mechanics excels at describing the incredibly small world of particles, atoms, and their interactions, while general relativity perfectly describes the very large, scale structure of the universe, gravity, and the dynamics of massive celestial objects. Quantum gravity seeks to merge these two incredibly successful but seemingly incompatible theories into a single, cohesive, and consistent framework that works seamlessly for both subatomic particles and the grandest cosmic structures. Various theoretical approaches, such as string theory, loop quantum gravity, and holographic duality, are all actively being pursued as potential contenders to achieve this grand unification. However, a definitive, final answer has yet to be found. A successful theory of quantum gravity would not only explain what happens at the singularity deep within black holes, but also what truly happened at the very beginning of the universe. It might even reveal the true, fundamental nature of space and time themselves, unlocking secrets we can barely conceive of now. Wormholes, those hypothetical tunnels through space-time, might actually be entanglement made physical. Wormholes, which are theoretical shortcuts or tunnels connecting distant points in space-time, have long been a staple of imaginative science fiction. However, some physicists now propose that these exotic structures could be the geometric manifestation of quantum entanglement itself. In this intriguing idea, often summarized by the equation ER to EPR, Every entangled pair of particles could be conceptually thought of as being connected by a tiny, non-traversable wormhole. If scaled up to a cosmic level, this could imply that the very structure of spacetime is built from countless microscopic quantum links, with wormholes serving as their physical, visible representation. While still highly speculative and a subject of intense theoretical research, this concept offers a striking and elegant bridge between quantum theory and general relativity. It suggests that the fabric of the universe, the very medium we inhabit, might literally be woven from the invisible, mysterious threads of quantum entanglement. Quantum physics could ultimately be the key to understanding everything. Quantum mechanics already provides the foundational explanations for the behavior of particles, atoms, and molecules, which in turn form the bedrock of all chemistry and biology. It underlies the fundamental structure of all matter, dictates the flow of energy throughout the universe, drives the life cycle of stars, and even seeds the formation of entire galaxies. Yet, for all its immense success and predictive power, quantum mechanics still leaves us with profound, unresolved mysteries. These range from the perplexing nature of measurement and wave function collapse, to its challenging unification with gravity, and even deeper questions about the fundamental nature of reality itself. Some physicists strongly believe that a deeper, more complete understanding of quantum theory could unlock the answers to questions that span all branches of science. These could include why the universe exists in the first place, or whether it could have been fundamentally different. In this ambitious view, quantum physics isn't just one piece of the cosmic puzzle. It may very well be the overarching frame that holds the entire puzzle together.